Well, hey everybody. How you doing? It's good to hear. Good to hear. Thanks. Um, yeah, we're gonna try and get some math here going, and we don't know how it's gonna turn out, but that's okay. So I'm gonna start posting some videos here. This is in my backyard. Sun shining, so why not? Um, but we're gonna start posting some videos, and it'll be a little bit of me FaceTime, and then it'll be some of the notes the way that we normally take them in class. So you guys should be able to follow along pretty much the same way like we did, before the world was crazy. So yeah, pay attention to those. We'll post them via Google Classroom, and I can send them out via links and things like that. But I will also have, after I'm done with the notes, I will um, I will have the PDFs available for people to collect if they need to get them from the school or something like that. We can talk more about how that'll work, but I will get those figured out as well. But digitally is something you can get right away as soon as I post it. So anyway, here we go. Hey everybody, this lesson here is going to be on simplifying of radicals. Let's talk a little bit about what that means. Quick recap for my class, Mr. Reinhardt's class at Lockerall. The last unit we did was quadratics, and what we ended up with as far as answers go were things that were, something plus or minus the square root of something else, right? So 2 plus or minus the square root of 7. And we couldn't really do anything with those. So if we wanted to, we could solve the square root of 7 and write the decimals there and add it to the 2 and subtract it from the 2, that sort of thing. And we did that a little bit, but is there anything else we could do with it? Well, yes, that's exactly what we're going to be working on today, is we could take some of those answers and we could rewrite them in a simpler way, hence simplifying radicals, and see what those look like. So let's start with a quick example of what a radical is, and there it is. That's a radical symbol. Do you guys remember that? I was a big dummy, and I used the Ninja Turtles radical. Okay, sounded dumb, and now you're laughing at how dumb your math teacher is, but there you go. That is the radical symbol, and this is what it looks like with a number inside it. First example here, the square root of 28. Normally what we would do with these is we would look at it. Remember, the process for solving a radical or solving a square root is what times itself can equal the number that's inside there. So what times itself would equal 28? Well, in this example, it's not a nice number because it's not a perfect square. And so we couldn't just say, the answer is 4. Right? If it was the square root of 16, then the answer is 4. If it was the square root of 25, the answer is 5. That's simple. But when it's a square root of 28 and it's not a perfect square, it becomes a little bit more nasty. And so we need to figure out what else can we do with it. Just like the fraction 2 over 4. Nothing wrong with that fraction. It's just not simplified. Okay? So we could simplify it down to 1 over 2. Now, if it was 3 over 4, we could not simplify it anymore. It's done. And so that's how we would leave it. Well, this radical here, the square root of 28, is not simplified. So we could actually take this down just a little bit further and draw it out in a way that we could do other things with it is kind of the main idea. So what we want to think about is this idea of factoring. And if we remember what factoring is, it's basically we're trying to figure out what numbers can make up another one. So the number 28, what would be some of the factors? And yes, I do want you to kind of play along as we're going through the notes, as we're writing this down. Try and think of these answers in your head as we're going along. So I'm asking the question, what are the numbers that can make up 28? What can we multiply together to make 28? So you could say 1 times 28, which is great. But I'm going to show you why we don't want to be thinking in those terms. We want to think in terms of like 2 times something and 3 times something. So let me show you what I mean here. One example would be 4 times 7. Okay, 4 times 7 equals 28. Is there something else I can do with the number 4? Is it simplified? Or I should say, is it factored out entirely? Is the 7 factored out entirely? That's what you want to think about. So now that we've got 4 times 7, let's go a step further. Can I simplify out a 4? Or can I factor out that 4 into something else? Well, yeah, 2 times 2 equals 4. So I can do that right there. Okay, I've written this out. I am now at a stage where everything inside here is done being factored. What do we call that? If the numbers are done being factored, if they cannot be reduced anymore like that, we would call them prime numbers. So every number that's going to be inside this radical symbol here is a prime number. And this is exactly where we want to be. We want to see it written out this way so that we can then figure out what to do with it. Okay. If we look inside the radical symbol here, we can see that we have a 2 times 2, okay? If we remember how radicals work, we would say that the square root of something is what times itself equals that. So we actually have that right here. This 2 times 2 is actually something that we could deal with, because over here it was a 4. Could I solve the square root of 4? If I separated this out into the square root of 4 times the square root of 7, could I solve the square root of 4? Well, the answer is yes, right? What is the square root of 4? Well, the square root of 4 is 2, and so I could write that down in front of it. So here's actually what it would look like. The square root of 4 is 2. Okay, this may be a little bit of a stretch here, and I can explain that more as we go along. But when we get to this stage here, we want to see what can we pull out of it. So it's a little shortcut you could think about is I now have a pair of 2's. Well, for every pair of 2's that I have, I'm going to pull out one of them. So it's no longer inside the radical. I'm going to pull it out there. And the reason is because the square root of 4 is 2. Okay, so let's do another example, and that'll help. Can I do anything with the 7? No. That one is already factored out as low as it can go. So so that one's done. And this actually right here would be our final answer for this. This is the fully simplified radical. 2 times the root of 7. Okay. All right. So let's look at another example here. Square root of 30. Okay. Again, it's not a perfect square. So we would want to factor it out. So think about what those numbers are that could make up 30. Again, we don't want to say 1 times 30 because then that just puts us at needing to factor out 30 again. We could do 2 times something, so 2 times 15 would be a good one. Or we could do 5 times 6. It really just depends on how you want to do it, because if I did 2 times 15, then I wouldn't factor the 2 anymore, but I'd have to factor the 15. And then would there be anything else that I would factor? So that's something to think about here. This one here, I like to choose numbers that are closest together. So 5 times 6, and then I want to look at them and say, can I factor these any further? So can the 5 be factored? No, it's a prime number. What about 6? Well, 6 is not a prime, so you can factor that one. So that becomes 2 times 3. So now what I have is this number right here. Square root of 5 times 2 times 3. All of those are prime, so we're good. If we think back to our previous problem, what we did was we looked for a pair of numbers. Okay, and when we had a pair of numbers, we pulled that number out. Or when we were at this stage, could we find the square root of one of these numbers? Well, down here we have the square root of 5. Can I solve that? No. The square root of 2. No, I cannot solve that one. The square root of 3. No, I cannot solve that one. So actually this one here, the answer is what we had originally. Okay, so this is an example to show you you might not be able to simplify it any further. Okay, just don't be frustrated, but that's how it looks. Some of you are probably cursing my name saying, well, why did you make me do that work? Well, we figured out that we can't simplify it. And as we get farther along in here, as you get better at it, you'll start to see, okay, if I break it down and there's no pairs, I can't do anything else. Or if I can't, get a number that I can find the square root of, then I can't go any further. So you'll start to pick up on those little tips and tricks here. So this would be the simplified form. Okay, this would be the answer. So if you were to write this on a test, or if you were told to simplify the radical, you would want to take it down to its most simplified form. And what that means is that everything inside the radical can no longer be simplified. You cannot factor it down and then pull out or extract any of the numbers. Okay, so this one, we were able to extract a 2 from it. Well, this one, we were not. Okay, so that is how the simplified version looks. Okay, so let's take a look at another example here. Square root of 12. Again, not a perfect square, so therefore I cannot just find the answer of it right away without it being a decimal. So I want to think of what numbers can I make up 12 with, and I've chosen to pick the numbers that are closest to each other. You might like to start with 2 or 3, the lowest numbers you can, and just work your way that way, and that's totally fine. So in here, I chose 3 and 4. Okay, 3 times 4 is 12. 3, is that a simplified, fully factored number? Yes, it is. It's prime. What about 4? Well, no, with 4, I can do 2 times 2, so I would write it out like that. Okay, now I have the square root of 3 times 2 times 2. Now, like we did up here, we're looking for pairs. Can I extract a pair from this and put it on the outside? Yes, I can. The pair of 2's turns into 1 2 on the outside and the square root of 3. Again, it's because the square root of 4 is 2. Can I answer this right here? Yes, I can. The square root of 4 is 2. There is no square root of 3. That's a nice number. It's a non-terminating, non-repeating decimal, so irrational decimal, we would say. So that's why it stays. But this pair of 2's can be simplified, so we pull that out. So is this a simplified form? Can I reduce anything else inside here? No, I cannot, so therefore it is the answer. That is the fully simplified form. Okay, let's take a look at another example. I know we're cruising through it, but you guys have a pause button. So if you're not getting it, pause. And that's fine. And write down a question that you want to email me or something like that. Pardon me. So here we go. Question number 4, example 4 here, the square root of 72. Hopefully you're realizing this is not a perfect square. Remember, I'm hoping that you guys can memorize your perfect squares up to 15. That's the goal. At least 12 for certain, but up to 15 would be great. So 72, a little bit of a bigger number. So it might take a little bit more thinking here to get it done, but we can do this. Don't fret. I'm going to choose 8 and 9. Closest numbers together. Again, if you want to start with 2, you know that this one's divisible by 2 because it's an even number. You want to start with that? Go for it. Whatever process you want to do is fine. You just need to you want to make sure that you get down all the way to the bottom where there's no more factoring that can be done. In this case, 8 can be factored and so can 9. Okay, and so I can go 2 times 2 times 2, which gives me 8, and then 3 times 3, which gives me the 9. So now I have fully factored it inside of here. Okay, so again, I'm going to look for pairs. Okay, I have a pair of 2's that I can pull out, and I have a pair of 3's that I can pull out there. So I'm going to take that 2, put it out there, take the 3, and put it out there. Now notice that these are being multiplied because remember, everything in here is getting multiplied, right? These are all multiplication. So when I pull these numbers out, if I'm pulling multiple pairs, then they're going to be multiplied still. So on the outside, I'm going to end up with 6 times the square root of 2. I don't need to factor the 6 out. That's what I had right here. I am not required in simplest form to factor this number. The one that I want to simplify all the way down is the one inside the radical symbol. Okay, so this would be our simplified answer. Okay, if you are asking yourself the question, why am I doing this? What is the point of going here? Why is this better than this? We're going to answer that question later. We want to get this process down first before we can figure out what is it that we can do with these that gives us a good reason to do that. Okay, so let's take a look at another example here. This one looks different, right? It is slightly different than what we've seen. We've got the square root of 6 times the square root of 7. If I have a number like this, so the square root of 6 times the square root of 7, think of it like this. Square root of A times the square root of B. If I have this scenario here, I can put them under the same square root symbol. Nothing wrong with that, okay? They're both roots, so it both works out fine. Think of it like terms. Okay, 4x and 3x, I can combine those together. Okay, so think of it like terms, essentially. So now I've got 6 times 10 inside here, and then I'm going to factor out these numbers here. So my 6 becomes 2 times 3, and my 10 becomes 2 times 5. You may be thinking over here, well, I can't find the square root of 6 or 10, so isn't this one going to be fully simplified? Maybe I'm done. Well, if you think that, that's fine, as long as you continue it out and try and find the answer. Don't just say, well, I can't find the square root of 6 and I can't find the square root of 10, so therefore it must be fully simplified. Okay, don't do that. You can, if you're thinking that, you just want to run it out all the way to the end to see if you're correct, okay? Because what I've got in here is 2 times 3 and then 2 times 5. Can I rearrange these inside here? Okay, there's only multiplication, right? That's the only operation we see inside. And therefore, multiplication is what we call commutative, right? It doesn't matter which order they're multiplied in. 2 times 3 is the same as 3 times 2. Okay, so I could rearrange these all I want to. So if I rearrange them, then I could have my 2, we'll go back a step here. I could put my 2's together, right? So I could go 2 times 2 times 3 times 5. Well, what I see there is I have a pair of 2's. Okay, even if you don't rearrange them, you can see that there's a pair of 2's that you could extract. So pull out that pair of 2's, and what's remaining inside is 3 times 15, or 3 times 5, which makes 15. This one's done. Okay, I can't simplify this anymore. Sure, if I factored out the 15, I would get 3 times 5. But I can't then extract the 3 or extract the 5 because there's not a pair. Okay, and so this one is done. So getting down to here is the final answer here. So if you were thinking originally that when we got to the 6 times 10 that it could not be factored any further, well, then you would be wrong because we could still. Okay, so we need to run these out to completion here. Okay, so again, if it's written like this, we can put them together. Okay, it still works out just fine. All right, so let's take a look at 6 here. Again, a slightly different question. we've already got some that look like they are simplified in a way. So let's see what we can do with these. What do you guys think? Can I rearrange these? Are they set up in a way that I could do anything else with them? What do you guys think? Take a second and think about what you could do. Hit the pause button and see what you think you could do. If you did this, then you are correct. Okay, you can take the two, all of this is multiplication. 2 times the square root of 14 times 5 times the square root of 21. So I could multiply all this stuff like that. I could rearrange it how I want to. So I'm able to simplify some things already. I could take the 2 times 5 and I could simplify that. And then the 14 and the 21, I could start factoring and see what I get from there. So let's go ahead and do that. Well, the 2 times 5 is 10. And the 14 becomes 2 times 7. The 21 becomes 3 times 7. And hopefully you found or noticed that we have a pair of 7s. So I'm able to extract one of those 7s from there. Okay, and so that's what's happening here in this next step. I've taken the pair of 7s, I've extracted it to the outside, and then the 2 times 3 that was still in there, well, I'm going to multiply those together to make 6, because I can't factor them out at all. They weren't a pair of numbers. So now my simplified answer, is this my simplified answer? No, it's not, because we need to simplify what's on the outside, 10 times 7. So this would be my simplified answer, 70 root 6, or 70 times the root of 6. Okay, let's do one more. We're going to throw in some variables. Okay, the variables here, you're actually going to find are not going to work any differently at all. When we want to factor the numbers, it's the same thing as when we're factoring variables. So, square root of 45 times a to the third power. Well, what can I do with the 45? How can I divide that out? It's not divisible by 2. It is divisible by 3, so I could go 3 times 15, or I could do 5 times 9. Okay, and then I could simplify that out. But if I did that 5 times 9, then it would still simplify out here. If I did 3 times 15, it would still end up with 3 times 3 times 5. Hopefully, over the course of these steps here, you guys have figured out some little tips and tricks, and you got that. And notice what happened with the a's. A to the third power becomes a times a times a. This is important as well, because what was the thing that we were looking for when we got to this step? When we were, well, not necessarily this step, but this step up here. What were we looking for? We found it here. We didn't find one here. We found it here. We found them here. We found it here. And we found it here. They were pairs, right? So we want to look in this step right here and see what pairs we have. Okay, well, I have a pair of 3s that I could extract, and then I have a pair of a's that I could extract, right? I take this 3 and I put it to the outside. I take these a's, take the pair of a's, and it turns into a single a on the outside. So I have 3a on the outside here, and what's remaining is the 5 and the a, and that just goes in there, okay? And that was our final answer there for that one. Sorry that I skipped ahead on you. I cannot reduce this any further, right? 5 is a prime number, and then a by itself is essentially prime. You don't need to think of it as prime, but it is. There's only a single a, so you can't pull it out of there. We're not going to pull out the square root of a. So this is the fully simplified answer. So even when we throw in variables, it'll work the exact same way. Okay? Okay, wow. It's been a little bit here. So I'm going to break this up into 2 little parts. You're going to pause the video here. You're going to stop the video, I should say. And then I'm going to post another video that you guys can look at, because I'm going to give a little worksheet for you guys to solve. And it's going to include some of these ones here, and then it'll include a little bit more near the end. So stay tuned. Okay, so this is going to be part 2. So this is where we left off right here, simplifying radicals. We found that these were our simplified answers here at the end, and then the last thing that we did was we threw in the variables there. So the next part is going to be a little bit more advanced. We're just going to kind of take it further here with these variables here. So let's look at the square root of m to the 7th power. Okay, well, what did we do in the previous one? Let me go back here. What we did was we had a to the 3rd power, and it became a times a times a. So looking at this one, what do you think it is? M times m times m times m times m times m times m. All right, there's going to be 7 of them. Okay. So then what am I looking for when I write these out? Pairs, exactly. We're looking for pairs. And so, hey, we got a pair right here, a pair here, and a pair here. So we have 3 pairs. So I'm going to pull out an m from this one, an m from this one, an m from this one. Or an m for this pair, an m for this pair, and m for this pair. Okay, so that would be m times m times m on the outside. And that would leave me a single m on the inside. Well, m times m times m is m to the 3rd power. And then m on the inside of the square root. So is anybody sitting here looking at it going, hey, I think I've got myself a little shortcut? Okay, if you do, keep thinking about it and let's see if it will work. Remember, shortcuts aren't bad. We just got to make sure that they always work. Okay, so let's discover it a little bit here. We've got n to the 20th power. So how many n's are going to be inside there? Do we really want to write out n 20 different times? No, we don't want to write out n 20 different times. So let's see what we could do. If we had n written out 20 times, how many pairs would there be? Well, hopefully you came up with 10. Okay, there would be 10 pairs of n's if we had 20 of them written out. So every time we have a pair, we pull one of the n's out. Well, how many n's would be pulled out of that? 10, exactly. So the answer is going to be n to the 10th power. Is there going to be anything after this written inside a radical symbol? No, there's not, because there is nothing left inside. Remember, all of them got used up. If we had written out 20 different n's, then we would have a line under each pair. That would mean that there is no single n at the end of it, because every one of them would be paired up. Okay, so we could pull out 10 of them. So if you were thinking of a shortcut here, did it still hold true? Okay, we're going to talk about the shortcut here in a little bit. Let's take a look at this one. X to the 51st power. Okay, a lot more. Yes, and don't write out x 51 times. Okay, that's not what I'm asking you to do. Hopefully the shortcut is making sense to you guys. If you haven't thought of it yet, then we're going to talk about it. What we did up here was we had 3 m's that we were able to pull out. It was originally m to the 7th power on the inside. Well, how is that 3 related to the 7? We had 3 pairs with 1 remaining. Okay. If you think of it as in terms of what is the next lowest even number. So the next lowest even number from 7 would be 6. Well, in 6 m's, how many pairs are there? 3. So if we take this number and we go down to the nearest even number and then divide it in half, that tells us how many pairs or how many m's we can pull out. So this one here, is it already an even number? Yes, it is. So cut it in half, and that's how many pairs we have. So this one here, this is an odd number, 51. So let's reduce it down to the nearest even number, 50, and then divide it by 2. What would that be? 25. So if we have 25, that goes on the outside. Well, what is remaining on the inside then? Because we have something left over. If we had to reduce this, we still have one left over. If we had 51 x's written out, then 25 pairs we would create, and then there would be a single x at the end of it. Well, we would have x on the inside. Okay, so the shortcut ends up being very simple here. All we need to do is go to the next lowest even number and then cut that number in half, and that's how many we get to pull out. Okay, so let's take a look here. Let's throw these all together before we get back into trying to do the shortcut again. Let's throw these all together. So we've got the square root of 18 times a to the 6th times b to the 5th. So let's take care of the 18 first. What are the numbers that we could multiply the 18 or multiply to get 18? Well, you could do 2 and 9, and then the 9 could be 3 times 3, so we'd have 2 and 3 and 3, and then a to the 6th and b to the 5th. Notice that I didn't write them out. We don't need to do that. If we've got our shortcut up here, you don't need to keep writing them out. If you're doing this by hand, you do not need to go through the process of writing out each of these. If you can figure out how many pairs are going to be in here, then don't worry about writing them out. Okay? If you want to, please do. If it helps you to keep it organized, then do it. Again, it's not for the purpose of trying to get you confused. You want to do what you can that will help. So, I know how many pairs are going to be in here. There's 6 of them. Okay, 6 A's. So how many pairs is that? Well, it'll be 3. This one over here, there's 5 B's. So how many pairs can I find in that one? 2. 2 pairs are going to be found in here. So I've got a pair of 3's. I've got 3 pairs of A's, and I've got 2 pairs of B's that I can pull out. So there's the 3 right there. There's the 3 A's, and there's the 2 B's. And what that leaves me with is a 2. And there's no more A's because that's an even number. And then there was a B because that's an odd number. Okay, so 3, A to the 3rd, B to the 2nd, square root 2B. If you're sitting here going, Mr. Reinhardt, that looks way more confusing than the other one. Again, we have not yet gotten to where we are going to do things with it. Right now we are learning the process on just simply how to simplify and how to get there. So follow this process along. We're going to step up into it. Okay. All right, let's look at another one here. Ooh, fractions. Ooh, gosh. I know everybody hates fractions. But if we remember some simple things that we can do with fractions, it's really going to help us out. So we have 2 in the square root of 7 on top, and then we have a square root of 2 on the bottom. Okay. Looks a little bit crazy, but we can do some things with it. If you remember, I've talked before about how we can always multiply by a 1. Multiply by a 1. Now, remember, what does 1 look like? It can be a single number, 1. But couldn't the number 1 also be represented as something like x over x? Remember, anything divided by itself is 1. Couldn't it be, 20 over 20 or a million over a million? All of those equal 1, don't they? Could it also be a radical number, for instance? Could it be square root of 2 over the square root of 2? Does that also equal 1? Okay, it does. And so let's see how that can help us, because I would like to get rid of the fraction here. If I can, I want to get rid of it. Well, the only way to get rid of it is to try and take care of this number here. So I want to multiply this entire fraction by the radical that was on the bottom. Okay, our rule is that we're not going to have any square roots on the bottom here. That's something we're going to need to follow. So we're going to multiply by this number written as a 1. Well, that's what square root of 2 over square root of 2 is. So what happens then when we multiply fractions, how do we do that? We multiply straight across. Okay, please remember that. We multiply straight across. So I'm going to take 2 times the root of 7 times square root of 2. That's going to be on top. And then on the bottom, it's going to be the square root of 2 times the square root of 2. Hopefully you guys are thinking about what happens on the bottom. Square root of 2 times the square root of 2 is 2. Okay? Square root of 2 times the square root of 2 would be square root of 4. Well, the square root of 4 is 2. So this actually ends up being very nice, very simple here. Okay, up on the top, the 2 is on the outside. Square root of 7, square root of 2, well, that would be 2 times 7. Okay, so there's that. So this is now the multiplied version of this. Is there anything else that we can do here? Okay, can we do something inside the radical symbol? The square root of 14, can we reduce that at all? The answer to that is no, we cannot, because the square root of 14, or if we tried to factor that, we would get 2 and 7. Both of those are prime, so that's done. But there is something we can do with this one. We can simplify these outside numbers here. Okay, 2 over 2. So the 2 over 2, but that becomes a 1. 1 times the root of 14. So is there anything else to be done here? Yeah, we don't need the 1 in front of it. Okay, 1 times anything is itself, so we don't have to keep that there. This would be the simplified version. Okay, this would be the simplified version. So let's do another example and see what we can come up with here. Number 13. All right, 5 times the root of 10 over the root of 6. So we want to get rid of this root on the bottom. So what do? We multiply it by a 1. So let's multiply it by a 1 that has the square root of 6 in it. Okay, that's how that looks. Okay, and then we know that this kind of, the roots go away essentially. Square root of 6 times square root of 6 is 36. And what's the square root of 36? 6. So that makes that simple. The 5 stays on the outside, and then we've got 10 and 6 on the inside. Okay, we would then factor the inside just like we did before. In fact, we had that same number right up in here. Okay, I know that I just jumped back for you, and you're probably like, whoa, what happened? But we had this one right here. I'm going to jump back again. Okay, so bear with me. Let me get to it. Bip, bop, bip, bop, 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 bop. This is how I act in class. Okay, so we have factored it. We're now down to here. We've got a pair of 2's that we can extract, right? So we do that. We get 5 times 2 up in here, which would be 10. But I want you to think about something. We want to reduce this, right? If I had 10 over 6, could I divide those both by something? Is that reducible? Think of a fraction, 10 over 6. Yes, it is. I could divide them both by 2. So 10 divided by 2 is 5, and 6 divided by 2 is 3. So I'm able to reduce that out there. This would be my final answer right here. Okay? Let's do it again. Here's what it's going to look like in this one. Now, this one, you're like, oh my gosh, Mr. Reinhardt, I really hate you. I really hate you. Now, this is the second part to the video before. If you wanted to take a break before this one and do it, that's fine. This is meant for an entire week's worth of math here, so don't fret thinking this is all done in one day here. But let's take a look at what we can do. So, again, we don't want any roots on the bottom. Well, we got a root right here, okay? What we did in the previous over here was we wanted to multiply by the root that was on the bottom. Okay, so square root of 6 over square root of 6. Well, let's do the same thing over here. Okay, what is on the bottom here? Remember, this is a grouping symbol. We've got parentheses there. So the entire thing on the bottom is 3 plus the root of 5. Okay, we always want to multiply by a 1. That's the rule we need to think about. Always multiply by a 1. So whatever we're multiplying by, it must be equal to 1. It's got to be the same thing on the top as it is on the bottom. Now, you may be thinking, let's go 3 plus root of 5 over 3 plus root of 5. If you do that, you're going to find out that you aren't actually going to get rid of the root. Okay? Do you guys remember the word conjugate? We talked about what conjugates are. Okay, that's when we had monomials and binomials. When we were talking about a binomial here, so it's something like 3 plus a, the conjugate of that would be, or the grouping of 3 plus a would be 3 minus a. So I actually want you to take the conjugate of this one right here and then multiply that. So here's what it's going to look like. Okay, the conjugate of 3 plus the root of 5 would be 3 minus the root of 5. Okay, this is still a 1, so this is still a legal math move. Okay, you're not breaking any mathematical laws here. Okay, but you'll find the reason why we wanted to do the conjugate as opposed to the exact number here. So when I multiply these out, I want you to think about the foiling. Okay, so over here we would FOIL these numbers. So it would be 3 times 3, and then it would be 3 times negative root of 5, and then it would be root of 5 times 3, and then it would be root of 5 times negative root of 5. Okay, that's how foiling. Remember, firsts, and then outers, and then inners, and then lasts. Okay, that's what foiling is. If we were to do that and they were the exact same number, then we would end up with a root right in between here, because 3 times 3, that's 9. What is the root of 5 times the negative root of 5? Well, it would be the negative root of 5 times 5, 25. Well, what's the root of 25? 5. So we get that. So this is how this one would simplify here. But if this was a positive symbol, then we would have the 3 times 3, which is 9, and then root of 5 times the root of 5. So that would end up being a positive 5. But then we would also have to have another root in here, where we would have 3 times the root of 5 plus the 3 times the root of 5. And it would just be nasty. So we're not going to do that. We wanted to multiply by the conjugate. Okay? It eliminated that root symbol there for us. So this one's simple. Now we just go 9 times 5. We'll do that in a second here. On the top, 2 times 3, and then 2 times the negative root of 5. So that's how this simplifies up there. It's a lot simpler than what happened on the bottom. Okay, we're going to do more examples of this. I know that's confusing and hard to follow. But remember, you got a pause button, so don't forget to use it. Okay, so 9 minus 5, that reduces to the 4. Okay. Are these two numbers right here like terms? That's the question. Can I just go 6 minus 2? I can't, because it's not 6 minus 2. This is actually 6 minus 2 root 5. Think of it as the same thing as 6 minus 2x. Okay? This right here is an entire term. 2 times the root of 5 is one term. So this is 6 minus 2 root 5. I can't just say 6 minus 2 and then put that root 5 there, okay? So without combining them, I need to still be able to simplify if I can. Well, I'm dividing everything by 4 here. I can simplify 6 over 4 and 2 over 4. That gives me, right, I could divide them both by 2, so 6 over 4 reduces to 3 over 2. 2 over 4 reduces to 1 over the 2, okay? So that is how that reduces there. Okay, I know, confusing. Let's do another one, and we'll just kind of see how we go. Okay? All right. This thing over here, this is a different way to understand it. Okay? So think about going from this orange step over to the blue ones. Forget about the answer right here. So 6 minus 2 root 5 over 4 would be the same thing as saying 6 over 4 minus 2 root 5 over 4. Well, I could reduce both of these down, right? 6 over 4 becomes 3 over 2, and then 2 over 4 becomes 1 over 2. And then if I subtract them out, then we get this answer here. Okay, so that's just a different, this right here is just a different way to understand what we did right here. Okay, so let's look at the next example here. Again, we've got this root on the bottom. We need to take care of it. So what can I do to take care of that root? Look at what we did in the previous example here. okay, we wanted to multiply by the conjugate of this. So what would the conjugate of 4 minus root 2? Okay, well, that would be 4 plus the root 2. Okay, that needs to be written as a 1, so make sure it's the same on the top and the bottom. And then we're going to multiply it out just like before. So 4 times 4 is a 16, and then root 2 and root 2, well, negative root 2 and root 2 just turns into a negative 2. Notice that the root symbols go away, okay? Think about the foiling method, okay? Up top, 7 times 4, and then 7 times root 2. That's what we get right there. Do a quick simplify of, on the bottom, 6 minus 2 is 14, okay? And again, just like we did up here, we want to take it from this step and reduce it down. So 28 over 14 and 7 root 2 over 14. Well, let's do that simplification there. Both of these can be divided by 14, actually, so that's nice. And the 7 over 14, that can be divided there, but it can't be divided by 14. So let's look at what we can do here. I can't just go 28 divided by 14 and 14 divided by 14 because I need to think of the 7. I need to think of what they can all be reduced by. They can all be reduced by 7, not by 14. So I'm going to take 28 divided by 7, that gives me 4. 7 divided by 7 gives me 1, and then 14 divided by 7 gives me 2. So this would be my answer here. Okay. Now, if you are sitting here thinking to yourself, Mr. Reinhardt, we've got a 4 over 2 right here. Can I keep reducing that? Well, the problem is that it's not just the 4 over 2. There is a 1 right up in front of here. Okay, so this is 4 over 2 plus 1 root 2 over 2. Can I reduce 1 root 2 over 2? And the answer is no, because that fraction is fully simplified. Okay, so this is our final answer right here. I cannot reduce the 4 over 2 because there is a 1 right here. So this fraction would be 1 root 2 over 2. Okay, so that one's done. Okay, that was a whole lot to take in. A whole lot to take in. 2 videos, a lot of stuff. This is a week's worth of mathematics. What I'm going to do is I'm going to start giving you guys some worksheets, and it's going to have some problems like this that you're going to solve. I will, near the end of the week, I will either post the answers to it, or I will, we can do a Zoom meeting or something like that that has answers to it. But anyway, this is the work that you guys are going to need for it. So I'm going to tell you to just do your best. And if you have any questions, send me that email. You've got my email. You got Google Classroom. You can contact me that way. In the meantime, just stay safe.